Okay, let's unpack this. Have you ever wondered what truly goes on behind the scenes, deep within the code and data, to build one of these cutting-edge AI models? The ones that can understand both text and images.
It's moving so fast. And today, we're doing exactly that kind of deep dive. We've got the technical report for ERNIE 4.5.
Ah, yes, the new one from Baidu.
Exactly. Released just, June 29th, 2025. It's a significant, multimodal, large model. And what's really great is having the full technical report. It gives us this rare, detailed look under the hood.
Like reading the lab notes.
Pretty much. It's structured like an academic paper, which is perfect for us. Our mission today is to walk you through its core components, really sticking to that structure from architecture all the way to deployment.
Right. And our goal here is to pull out the really important bits, give you those aha moments. We want to make sure you walk away knowing what makes ERNIE 4.5 tick. But, without getting lost in super dense jargon, we're breaking down a complex paper into something digestible.
And it's definitely worth mentioning that parts of this are open source.
Oh yeah, GitHub, Hugging Face. That's huge for researchers and developers listening. It means people can actually use and build on this stuff.
Definitely.
So, okay, like any good research paper, you start with the foundation, the blueprints. Let's talk about ERNIE 4.5's architecture. What's the core design here? What makes it different?
Well, at its heart, ERNIE 4.5 uses something called heterogeneous mixture of experts, MOE for short.
Mixture of experts, right? We've talked about that concept before, like having a team of specialists.
Exactly like that. Different experts are trained for specific data types, text, images, and the system smartly routes the information. But the key here is heterogeneous.
Meaning they're not all the same size or type?
Precisely. They have this really innovative modality-aware expert allocation strategy. Basically, the visual experts, the ones handling images, are designed with only 1/3 the parameters of the textual experts.
Okay, hold on. 1/3 the size. Why?
It seems to be about efficiency and how visual information is processed. Maybe it doesn't need the same parameter density as complex language. It's a smart optimization.
Yeah, that avoids just throwing massive compute power at everything equally. It sounds much more nuanced.
It is, and it tackles another big challenge with MOE, especially multimodal MOE, router instability.
Router instability, meaning the part that directs traffic gets confused.
Kind of. If you just bolt image capabilities onto a text MOE model, the router can get overwhelmed or collapse, as they call it. This actually hurts the model's original text abilities.
Ah, so adding vision could break language. That's not good.
Not at all. So ERNIE 4.5 uses a modality-isolated routing strategy. They found textual experts tend to have very focused, concentrated activations, while visual experts are more dispersed. Keeping these routing paths somewhat separate prevents that collapse and keeps everything stable.
Interesting. So the system learns to keep the specialists focused on their domain, even when handling mixed inputs.
That's the idea.
This is where it gets really interesting for me. It's not just mixing data. It's fundamentally rethinking how the model processes different information types to be stable and efficient. So what are the big wins from this heterogeneous MOE design for, the end result?
Well, there are three main advantages highlighted. First, unified multimodal modeling. They can jointly optimize all the parameters, text and vision together, which lets them scale up massively. They mentioned hundreds of billions of parameters.
Wow, okay, big scale.
Second, routing stability. We just talked about that it makes the model reliable. Plus, they can actually introduce the vision experts later in training, which saves compute, because vision often builds on language understanding anyway.
Right, learn language first, then vision. Makes sense.
And third, computational efficiency. If you're just doing a text task, the model can simply skip the visual experts. Saves memory, saves time. And for tasks using both, they use modality-aware partitioning to allocate resources smartly.
Got it. Efficient and stable. The report mentions other bits too, right? Vision encoder, adapter.
Yeah, it just lists things like a vision encoder, an adapter, multimodal position, embedding in the table of contents. While the excerpt doesn't detail them, those titles clearly point towards making sure all these different data types integrate smoothly.
Okay, so that's the architecture, the blueprint. Now, you need the building materials, the data. How do you feed a beast like this? Especially when the report mentions this scarcity of high-value data.
That's a huge bottleneck in AI right now. High-quality, well-aligned data is hard to come by. ERNIE 4.5 approach is pretty aggressive. Data synthesis.
Data synthesis. So they're creating data.
Yep. They don't just collect, they generate. They use a key point-based Bayes synthesis method. Imagine taking concepts from textbooks or educational websites, say math problems, historical facts, code snippets, and using those as seeds to generate tons of diverse, high-quality examples.
Wow, so they're basically crafting the perfect curriculum for the AI, not just scraping the web and hoping for the best.
Exactly. It gives them much more control over the quality and diversity of the training material. And for reasoning specifically, they go even further.
How so?
They perform targeted processing steps on reasoning-related corpora. That means selecting good examples, organizing them by the type of reasoning needed, grading the difficulty, filtering out junk. It's meticulous work to boost logical thinking.
Okay, that sounds incredibly labor-intensive, but probably necessary for complex reasoning. What about mixing text and images? That's core to multimodal, right?
Absolutely. For that interleave text-to-image data, which you need for understanding things like articles with pictures or web pages, they tackle the limitations, limited scale, weak alignment by systematically collecting web data, but also extracting content from videos.
From videos? How?
Keyframe extraction, grabbing important still images, and automatic transcription to get the corresponding text. It's a way to generate more of that rich interleave data.
Clever, but standard image text pairs, like photos with captions, are notoriously noisy, aren't they? Generic captions, irrelevant stuff.
Oh, definitely. That's a major headache. The report calls out noise like irrelevant descriptions, generic captions, and redundant images. Their solution involves strong filtering techniques. They use things like CLIP score thresholding.
Which is like an AI quality check, making sure the text and image actually match meaningfully.
Exactly. Plus deduplication to remove repeats. They also use image classification and tagging to sort images, and even recaptioning, using AI to write better captions for existing images to improve that text-image alignment.
Recaptioning, using AI to fix data for AI. Interesting loop.
It is. And one really unique strategy they mention is stitching multiple images into a grid layout. This specifically trains the model to understand things presented in grids, like maybe comic panels or comparative product shots.
So, boiling this down, they're not just data hoarders, they're data crafters. Curating, filtering, synthesizing, even fixing existing data to make sure the model learns precisely what it needs. That's a massive effort.
It really is. And it extends to specific domains, too.
Like industry or healthcare.
Yeah, for domain-specific data, industry, finance, healthcare, entertainment, they use progressive mining to keep finding relevant data and conditional pre-training schemes, especially for things like creative writing, to learn more efficiently. They even use ASR automatic speech recognition on video soundtracks and podcasts to pull out domain-specific audio info, then clean it up for training.
Okay, a truly comprehensive data strategy. So they have the architecture, they have the meticulously prepared data. How do they actually train the model? What's the pre-training recipe?
It's a three-stage training process, according to the report. Stage 1 is text-only training. Build that strong language base first.
Makes sense.
Stage 2 is vision-only training, focusing purely on visual understanding. And then Stage 3 is joint multimodal training, where everything comes together and the text and vision parts learn to cooperate deeply.
Text, then vision, then both. Logical progression. Are there specific optimization tricks they use during this?
Yes, a couple of key model optimization techniques. One they highlight is router orthogonalization loss. Remember the MOE router. This technique helps ensure the different experts really do specialize and don't overlap too much. It forces them to be, well, orthogonal in a mathematical sense.
And that actually helps performance.
Significantly. They report it improves scores on the MOU benchmark from 50.2 to 53.1. That's a noticeable jump just from making the experts more distinct. They also use something called token balance loss.
Wow, okay. A smart trick for better specialization. What else? Any innovations in just managing the training process itself, like the learning rate?
Yes, this is quite interesting. They use an exponential moving average, or EMA, approach. They found that using a continuous EMA throughout pre-training worked just as well as traditional learning rate decay, where you gradually reduce the learning rate over time.
So, no need to fiddle with learning rate schedules.
Essentially, yes. They call it a decay no more approach, which simplifies things. And they engineered an asynchronous online EMA mechanism. It offloads parameters to the host memory for frequent EMA updates without slowing down the main training loop. That specific mechanism is actually one of the things they've open-sourced in PaddleNLP.
Very cool. Simplifying training while maintaining performance and sharing it. Okay, so pre-training gets you a powerful but maybe somewhat raw model. How do they refine it? Make it align with what humans actually want? That's post-training, right?
Exactly. This is where you fine-tune the model for specific capabilities and, crucially, safety and helpfulness. First, for the language model side, they mentioned this clean separation capability.
Meaning?
After all that multimodal pre-training, you can actually strip out the vision parts, the multimodal experts, vision encoder, adapter layers, and you're left with a high-performance text-only LLM. It's sufficient for deployment if you only need language.
Neat trick. Okay, what about the fine-tuning itself?
For supervised fine-tuning, SFT, they collected a large dataset, 2.3 million samples, and categorized it. They separate reasoning data, needing complex, step-by-step thought processes, extended chains of thought, from non-reasoning data, where it's more about factual accuracy or conciseness. They train on this for 2 training epochs.
2.3 million examples. That's a lot of specific instruction following. How do they reward the model during the next phase, the reinforcement learning, especially with these different task types?
That's where the unified rewarding system is key. It's designed to handle both reasoning and non-reasoning tasks using different reward signals.
Okay, break that down. How do you reward reasoning? That seems hard to measure.
It is. For reasoning tasks, they use rule-based verifiers for things that have clear right-wrong steps. But they also rely heavily on AI judges. They use reference-guided LLM as a judge, or RLLM.
So one AI grades another AI's reasoning against a correct answer.
Exactly. They also use a sandbox environment to safely test code execution for programming tasks. And there's the Reference-Guided Discriminative Reward Model, RDRM. Think of this like an open book test. The reward model gets access to the reference answer, helping it judge not just correctness, but also the quality and structure of the reasoning.
Okay, that sounds thorough. Verifiable rewards are crucial. This really gets at the question, how do you make an AI genuinely think and understand complex inputs, especially images, in a way you can trust? This seems like the secret sauce.
It's definitely a core part of it. For the non-reasoning tasks, which might be more about style or helpfulness, they use different tools. Checklist-aware verifiers, checking against explicit criteria, generative reward models, GRM, providing more nuanced multidimensional feedback, and standard discriminative reward models, DRM.
So a whole toolkit of reward methods and the reinforcement learning process itself.
They filter the data used for RL, removing prompts where the model consistently fails or shows little variance, to focus training effectively. They also use reward normalization across different topics to keep the training stable. And importantly, they mix reasoning and non-reasoning data during training. They also use an experts merging strategy.
Merging experts.
Yeah, they transfer multimodal experts learned during non-reasoning training over to the reasoning models. It's inspired by techniques like DeepSeek's Chimera, helping to combine strengths and overcome cold start challenges when teaching the model complex multimodal reasoning from scratch.
Fascinating. Combining specialist knowledge. Now, what about the vision side specifically? How do you fine-tune for tasks that really need sharp visual perception?
That's post-training of VLMs, vision language models. The big challenge here again is data scarcity, especially for dense image caption pairs needed for tasks like visual puzzles, geometry, chart reading, things requiring fine-grained understanding.
Right, you can't just rely on standard web captions for that.
Exactly. So again, they turn to synthesis. They synthesize a large volume of perceptual data, programmatically generated geometric figures, math functions, puzzles. This gives them perfect visual text pairs with fine control. They also complement this with recaptioning natural STEM imagery from the real world.
Synthesis again, but this time for highly specific visual tasks. And the reward system for vision.
They use reinforcement learning with verifiable rewards, RLVR. For visual STEM tasks, they might reformat multiple choice questions into open-ended ones that require showing work, and they filter these based on learning progress. For visual puzzles, they synthesize a data set of over 10,000 puzzles. The evaluation here is clever. They use 2 other LLMs to judge the model's puzzle-solving attempt. One checks the internal logic, the other checks the final answer.
Using 2 AI judges for visual puzzles? That's intricate. Okay, building this thing is clearly a massive undertaking, but making it run efficiently and reliably, especially at scale, that's a whole other mountain to climb. The report dives into engineering, right?
Oh, yes. Sections 5 and 6 are all about efficiency and deployment. A big one is FP8, mixed precision training.
FP8. Using even fewer bits for numbers than the usual BF16 or FP16.
Exactly. Having the bit width. The benefits are pretty clear. Improved computational throughput, reduced memory consumption, and decreased communication overhead. Faster training, less memory needed.
What are the engineering tricks to make FP8 work well? It can be tricky.
Key insights they mention are fine-grained memory optimization, carefully managing which activations need to be kept in higher precision for the backward pass, and FP8 communication optimization and overlap, performing network communication using the smaller FP8 format to speed things up.
It really sounds like they're squeezing every ounce of performance from the hardware. But training on, say, 10,000 GPUs, things must break all the time, hardware failure.
And that's a constant reality in large-scale AI. The report calls it elevated failure interruptions. Their answer is a framework-native fault-tolerant system.
Built right into the training framework.
Yes, monitoring across the model, the framework software, and the hardware itself for really robust fault detection and rapid recovery.
How do they detect failures quickly, especially subtle ones?
They have tools like TraceHang, which analyzes communication patterns to diagnose when training just hangs or freezes, and something really interesting called the online SDC scanner. SDC is silent data corruption, where calculation gives the wrong result but doesn't crash anything immediately. Very dangerous.
Like a typo in the matrix math that doesn't cause an error message. Yikes.
Exactly. Their scanner verifies computations during idle times in the training pipeline bubble times, using fixed inputs, catching these errors without slowing down training.
Clever use of idle time and recovery. How fast can they get back online after a failure?
This is where it gets seriously impressive. They use parallelized warm-up to quickly initialize the system after a restart. But the star is zero-cost checkpoint, ZCC.
Zero cost. How can saving a massive model state have zero cost?
It allows checkpoint saving at every training step without any overhead for training throughput. The trick is clever overlapping. On the framework side, it overlaps the memory copies needed for checkpointing with parts of the training computation that don't conflict. On the cluster side, it uses super-fast RDMA peer-to-peer transmission.
So it happens in the background without pausing training?
Essentially, yes. And
Yeah.
the result, they reduced the end-to-end automatic recovery time to less than 8 minutes for ERNIE 4.5 on their 10,000 GPU cluster, and they maintain over 98% effective training time.
Less than 8 minutes recovery on a cluster that size. That is absolutely a game changer. Think of the time and money saved, the progress not lost. Incredible.
It really is state-of-the-art for large-scale training resilience.
Okay, so it's trained, it's robust. Now, deploying it for actual use inference, how do they make it efficient there? People don't usually have 10,000 GPUs for running the model.
Right. Inference and deployment focus on efficiency and supporting diverse hardware. Quantization is key here.
Reducing the precision again, but this time for the final model.
Exactly. Making it smaller and faster. They offer options like BF16, FP8, and even more aggressive ones like W4A8, 4-bit weights, 8-bit activations, and 2-bit weight-only quantization. Plus, techniques for the KV cache and attention mechanism.
W4A8, that's pretty low precision. Does it hurt performance much?
That's always the challenge. They tackled issues like slow GPTQ on MOE, GPTQ is a quantization method, and handling outliers, extreme values that are hard to quantize. Their solutions include multi-expert parallel collaboration for better calibration and an outlier transfer algorithm to manage those tricky values. The result? Impressively small impact on performance. General tasks only drop by 0.49%, and reasoning tasks actually improve slightly by 0.11%.
Wow, almost no loss, sometimes even a gain for that much compression. That's huge for making it usable on less powerful hardware. What about 2-bit?
For extreme compression, they use 2-bit quantization with a method called convolutional code quantization, CCQ. It can get 4-bit models down to an equivalent of 2.75 bits, 3-bit down to 2.5, and potentially even lower.
Pushing the limits of compression. Any other speedups?
Yes, inference acceleration through optimized kernel's low-level code. Their W4A8 kernel acceleration gives up to 100% speed up on certain workloads. And their efficient attention kernel outperforms popular alternatives like Flash Attention 2 and Flash Attention 3, giving speedups of 1.68x and 1.48x, respectively.
Serious speed gains there. And deployment, getting it running smoothly.
They focus on deployment strategies like sophisticated load balancing across different types of parallelism, data expert, and even dynamic role switching, for instances, to make the best use of available hardware resources.
Okay, a ton of engineering deep dives there. So all this tech, the architecture, the data, the training, the engineering, does it work? The evaluation section must be packed. And how do they enable others?
First, on enabling others, they highlight their open source development tools, ERNIEKit and Fast Deploy. These are crucial for letting the wider community experiment with and deploy these models.
Right, that open source aspect is key for listeners who might want to try this themselves. Big deal, yeah. The results, the proof.
The report details evaluation and results for both the language-only aspects and the full multimodal model, comparing against many benchmarks. But honestly, sometimes the most convincing evidence comes from the qualitative examples they put in the appendix. seeing what it can do.
Yeah, the examples. Give us some highlights. What kind of things can ERNIE 4.5 actually handle?
They're pretty impressive. In OCR and document understanding, it can look at a complex image of Roman history notes and generate a structured mind map. Or read a medicine label and extract key info. It even converted a multilingual lab report image into an Excel spreadsheet.
Wow, turning an image of a table into a real spreadsheet. That's useful.
Very. And it shows deep understanding. It also has remarkable ancient Chinese character recognition. It could read small seal script and explain the historical context that's highly specialized knowledge.
Okay, that's niche, but shows incredible depth.
Yeah.
What about reasoning?
For reasoning cases, it solves visual puzzles that require deduction. There's a great example, Figure 26, where it analyzes a metaphorical image about machine learning depicting monsters and training processes and correctly explains unsupervised learning, supervised fine-tuning, and RLHF based on the visual metaphor.
Understanding a visual metaphor about AI itself, that's pretty meta and impressive.
It is. For visual reasoning, it can solve emoji quizzes, like figuring out the movie Up from relevant emojis, understand internet memes involving puns, like one with a horse and a QR code, or even do depth sorting, looking at a photo and correctly ordering objects based on their distance from, say, a teddy bear in the foreground.
Depth sorting from a 2D image. Okay, that requires real spatial understanding, code, creativity.
Yep, code synthesis. It converted a flowchart diagram illustrating the Collatz conjecture into working Python code, and image condition creative writing. Shown a picture of the inside of a fridge, it generated a plausible meal menu based on the visible ingredients.
Okay, those examples really paint a picture, from ancient scripts to fridge contents to coding. It's not just what it can do, but the flexibility and depth across text, images, and reasoning. That's the takeaway.
Absolutely. So to wrap it up, ERNIE 4.5 really feels like a significant step. It's the combination, the sophisticated heterogeneous MOE architecture, that incredibly meticulous data work curation and synthesis, the multi-stage training, the advanced post-training with those verifiable reward systems, and crucially, that hardcore engineering for efficiency and fault tolerance. It all comes together.
It's like a blueprint, as you said, not just a powerful model, but a demonstration of how these incredibly complex systems can be built robustly and efficiently. Which brings us to the final thought for you, the listener. When you see this level of integration, understanding text, images, code, reasoning, combined with this kind of engineering, making it stable and potentially more accessible, what new possibilities does that open up? How might AI, this advanced, this integrated, start to reshape our daily interactions with technology, information, and maybe even creativity itself?